Welcome to module 6 in programming in C++ again. We have already discussed the notion of constness in this module. We have discussed how in place of using manifest constant, we can use the const declaration to qualify a variable declaration, and how it does not allow us to change the value of a variable once it has been declared and initialized. We have also shown how constness works with pointers and talked about the constant pointer and constness of the pointed data. We will continue on that, and next we will talk about a related notion which is known as volatile. This volatile is a less commonly known concept. So, let us try to understand it a little bit. Let us think about a variable. So, what can we do with a variable? We can, after a variable has been declared, defined, possibly has been initialized, then we can read the value of the variable, or we can assign a new value at any point of time. And the basic property that we always program with is, if I have read the value of a variable, then if I read the value again, I am expected to get the earlier value itself, unless some new value has been assigned in between. So, if I assign a value and keep on reading n number of times, I will always get the same value till I make the next assignment. This is the basic concept of read write of a variable. Now, look at constness in this context. In constness, what we are saying, that we are allowed to assign, or in that sense initialize the value only once and not allowed to change it afterwards. So, for the whole lifetime of the program, the values that I read of this variable will be the same. That is the constness. Volatile in contrast is saying that it is a volatile value, which means that if I read a variable at different points of time, there is no guarantee that I will get the same value. I may get different values. So, even when I have not done any assignment to it. So, as the word volatile refers, volatile is something that evaporates something. So, suppose the value of the variable was 5, you read it once, then you did not make an assignment, but you read it after maybe 10 statements, or after a certain time, the value may be found to be 7. So, the original earlier value 5 has disappeared, has evaporated. So, that is the notion of the volatile variable. So, why is this important to have this kind of a variable behavior in program? Because there are some system situation where this can happen. For example, suppose I am writing a network programming code whose purpose is to keep listening to a port to find if some data has arrived. Now, if you, so what are you doing? You are not expected to write anything to that port, because you are expecting data from outside the system. So, you are only reading. So, what will happen when some data arrives, then your value will change, and that is, but earlier when you have read, the value was possibly null, then suddenly you read it after maybe 100 millisecond, you find that some value has come. You read it after another 100 millisecond, there may be a different value that has come, because another different packet has come. So, it is possible that a variable can be changed by the hardware, by the kernel of the operating system, by another thread and so on. So, it is required to model that behavior, and in C++, this is modeled in conjunction with the const concept, because one which kind of gives you absolute truth, and the other which gives you kind of no guarantee, that you just do not know what the value of the variable is. So, they are clubbed together, and we call them as CV qualifier, C for const, V for volatile, CV qualifier, and any declaration of a variable can be prefixed with a CV qualifier, const or volatile. So, we will show example of that. So, here we are trying to show how volatile could be useful. This is a code, very simple code which assigns a value 0 to I, and then tries to loop on the condition that I is not equal to 100. Now, if we just shown this code, you will immediately identify that this is an infinite loop. Why is it an infinite loop? Because if the value of I is 0, and then I am checking if I is 100 and I continue as long as I is not 100, certainly the value of I will never become 100. So, this condition will always remain true. So, this loop will continue indefinitely. So, what the compiler will do? Compiler will optimize and say that this is true, this is while 1, and simply that whole expression will go away. Now, let us say you qualify this by as volatile. You say this is a volatile variable I, and you write the same code. Now, it does neither gets optimized, and what you expect is this code will actually work, because you, being a volatile variable, you expect that there is some other agent, there is some hardware, some port, some kernel system, some thread possibly is changing it through some other means. So, you keep on waiting till its value becomes 100, and it is possible that at some point it will become 100, and then that particular condition becomes false and the function will be able to return. So, this is the use of the volatile variable in C as well. Okay. Let us now move on and talk about a different kind of use for hash define, which is again processed by the C preprocessor. We call them macros. The difference being that we still define them with hash define what? We have a name, but the main thing is we now have a parameter into this. So, what happens is when I use it with a parameter. So, we are saying that square is the defined name, and I am putting a parameter a to it. The effect of that is the C preprocessor will directly go match a with x and replace all x's in the defined expression by a. It is simply a text based substitution. So, wherever it will find x in that expression, it will substitute it with the parameter a. Now, macros are a very commonly used feature in C, and we are also useful in C++, but what it kind of allows us to write a function like notation. So, if you are not told the hash define line, and if you are just reading the main, you will not know whether square is a macro or it is a function. It could pretty well be a function. But when it comes to the compiler, again like in the case of manifest constant, the compiler was not being able to see that it is a variable, it was just seeing the constant value that you have written or the constant expression that you have written. Here again the compiler will not be able to see any kind of a function notation, you will simply be able to see the expression that the CPP has replaced. So, macros have been very often widely used in C programming, and it has advantages, particularly in C you could not have done without macros for several reasons. It gives you efficiency also, because macros do not need a function call overhead, but they have a very serious pitfall. So, we show some of the pitfalls here in the same square example, and we are trying to, this is the macro, and here is just that I am trying to use it with a plus 1. Earlier I was using it with a, I am trying to use it with a plus 1. Certainly, if somebody reads it, the mental notion would be a 1 will be added to a, so it will become 4, and then it will be squared, so it will become 16. But when you run this program, you will actually get an output 7, and to understand that you will have to expand the macro. Now, expand this macro to this line. You can see that in the macro x is replaced by a plus 1. So, in place of x, if you just write a plus 1, it becomes a plus 1 star a plus 1, and then it becomes an expression where the precedence and associativity apply. So, 1 into 1 times a, which is in the middle, gets the precedence. So, that gets operated first. So, this practically becomes 2 a plus 1. So, it becomes 7. So, certainly this has caused all the problem. Fortunately, this is a problem which can be fixed if you just put parenthesis around every x or around every instance of the parameter in the macro definition. So, if you do that, how will it help? So, we can just see the expansion. This will help because now I have since the parentheses have been put, now in after the macro is expanded, in the last line of this slide you can see that there is parenthesis around a plus 1. So, it says a plus 1 into a plus 1. Now, the BODMAS rule say that the a plus 1 has to happen first, which is what we had expected. So, this can still be fixed. Let us go ahead and so what this is really disturbing, that if you have to remember that every time you write x, you have to put a parenthesis around that, otherwise you might get surprises. But next let us see an example where the situation is actually worse, because here, so now we have fixed the definition of the macro. Now, we are trying to use it again, and I want to use it with plus plus a. It's a plus plus is a pre-increment. So, if a is 3, as in here, if I do plus plus, I expect it to become 4. 4 should go to the square, it should get squared, it should become 4 times 4, the result should be 16. You try that, the result is 25. Why? Again, look into the expansion of this macro. If it is expanded, it looks like this, because there are 2 x. So, plus plus a is written for each one of them. So, what happens? Plus plus has the highest precedence over, is at a higher precedence than multiplication. So, both plus plus has happened before multiplication has happened. So, a was 3, it first becomes 4, then it becomes 5, and then the multiplication happens. So, the result is expectedly 25. The unfortunate part of the story is there is no easy fix for this in C. So, you will have to live with these kind of possible pitfalls in the macros. So, there is a new feature in C++ which is called as inline function. Let me first define what how to do this, and then we will explain how does it relate to the macros. So, an inline function is just another function, it is no special kind of function. Only difference is in the prototype of the function, in the header, you write the keyword inline before the return type. So, if you write this keyword inline, then what happens is when the function is called, the actual function call does not happen, but whatever code the function has, that code the compiler puts at the call site. That is the basic. So, the override of function call is avoided. So, we define the function, we prefix the function header with inline. Just focus here on the right hand side, which is the C++ code, left hand side is the original C code for your reference. On the right hand side, we have not doing a hash define macro, we are saying square is a function which takes x, returns x times x as an integer, and we are prefixing it with the inline keyword in front. The use code for this here and here remains same. Now, the advantage is that this is in C++, now this is truly a function. So, you cannot have any of the pitfalls that we were showing earlier, because it truly first evaluates the parameter and then takes that evaluated value and calls the function. So, if you pass here a plus 1, it will first make a plus 1 as 4 and then pass that. If you do plus plus a, it will increment a from 3 to 4 and pass 4. So, you are not going to get any of the pitfalls, but you get the advantage of the macro, that is with the hash defined macros you were able to avoid the override of function call, all the parameter copying, then transfer of control, then the computation, and then again transfer of control back and the copy of the return value. All these can be avoided because the compiler would try to actually put the x times x that I am doing here right at the site where the function has been called. So, that is the basic feature of inlining. So, inlining helps to get the benefit of macro to a good extent, while it protects the basic properties and the types of functions. So, if we can just compare them side by side, then macros are expanded at the place of call. Inlines are also in some way expanded at the place of call, but it is not possible to show that to you because macros are expanded in text form. So, I could illustrate that to you, but inline functions are expanded in terms of the assembly code or the binary code at times. So, it is not possible to understand it so easily, but we can just take it that it does the job right at the site where you have called. Both of them are efficient in execution, both of them bloats the code becomes fatter, because what is happening, you have one function defined, and if you are doing a macro, that function, that macro may have been invoked at 10 places. So, the whole macro code will be copied 10 times. Similarly, in inline function, if I have a function inline and that has been called at 10 places, the function body will occur at 10 places, the code will become bigger, which may not be a concern for some of the common software systems that we do, but may be a concern in other cases, like when we write programs for our mobile phones and handheld devices, where the memory is really small. If the program becomes larger, then it becomes difficult to fit that app. So, because you are concerned with the size of the app also, but we will not get much deeper into it. But the next point is, the macros have syntactic and semantic pitfalls. We have shown two of them. The A+1 was a syntactic pitfall, so we could manage it by putting parentheses around them. ++a was a semantic pitfall, because the way the ++ is executed, so we could not manage that, we had to live with it, but inline functions will not have any such pitfall. Certainly, macros do not check types for parameters, whereas inline functions do that. So, their parameters are robust. So, it is possible that a macro which is intendedly written for, say, an integer type of value may inadvertently be called or invoked with some double variable. The compiler would not be able to understand, whereas in inline function that is not possible, because it is just the function that we have. However, macros do have advantages. For example, the fact that it does not check for type help us to write some code where I do not know the type. For example, I want to write a code to swap two variables. Now, the code to swap two variables could swap int variables, could swap double variables, could swap char variables and so on. But if you were to write that in C++, the swap function, one swap function cannot do all this, because if I have to swap two int variables, then my parameters would be of int type. If I want to swap two double variables, my parameters will be of double type. If I want to swap two pointers, my parameters would be of pointer type. So, I cannot write that function easily in C++ and inline that, whereas I can write one macro and swap it, because macro is not checking the type, it will just check that there are two variables, as a third variable, 3 assignments, we know how to do swap, it will just put that code here. So, macros do provide some advantages, and going forward towards the end of the course, we will show that you can also do that with inline functions, but with the support of a very later feature of C++ known as templates. So, when we discuss that, we will show how to do this. Finally, for macros, there is no error checking done for compilation. In inline function, the errors are checked, and certainly, like the manifest constant, macros are also not visible to the debugger. You will not be able to see the square macro if you try to debug, because actually the compiler has never seen that square, because it was replaced by the preprocessor, whereas for inline functions you will be able to see all of that in the debug build. You will be able to, if you do a debug build, you will be able to see that. The difference that I should highlight here, that with inline function, one feature that the compilers do is, if you do a debug build, the inlining is not done. If you do a release build, the inlining is done. So, if you do a debug build, an inline function is just like any other function. So, you can debug into that function, because in the debug build you are saying, I want to debug, I want to look inside what is happening, whereas in a release or production build, you really want the efficiency to be there. You want that the code should run the fastest. So, you are not interested to debug anymore, you have already debugged, you know it is correct. So, that is when the inlining actually happens. It is a little bit subtle point, but please keep this in mind. Over time, you will slowly understand these factors. So, we would suggest that we always use inlining. There are, however, some limitations that you should be aware of. Inlining is called a directive. A directive in a language is a suggestion to the compiler. You are saying, you are telling the compiler, look, I think it is useful to inline this function, but it is not mandatory. It is not a binding on the compiler that it must inline. So, you may say inline, but the compiler may not inline the function. If the compiler finds that inlining it has problems or inlining it does not really help the efficiency. For example, a very simple example is, if a function body is very large, then what gain are you doing by inlining? Is that function call is not required, function return is not required. Rest of it, the computation has to be done anyway. If the function body is very large, then this additional overhead of call and return are very small. So, you do not want to get into all this trouble of inlining, but if the function body is very small, inlining really is. So, the compiler decides whether it wants to do inlining or not, and in many cases in C++, the reverse is also true, that you may not have said that a function to be inlined, but the compiler might inline it, finding that it is efficient to inline. Second point to be noted is, inline functions cannot be recursive, because what we are saying? We are saying that at the place of inline, at the face of function call, we will put the body of the function. If a function is recursive, the body itself has another call. So, at that call you will have to again put the body of the function, that will again have another call. Now, how many times will you put it? That depends on how deep the recursion goes, which you do not know till you have the values, till you know whether you are trying to do factorial 3 or you are trying to do factorial 77. So, you do not know how many times the inlining has to happen. So, recursive functions cannot be inlined, they will necessarily have to be a normal function. Since inlining is replacing the body, so in the third point I highlight the fact that if you want to inline a function, then the function body will also have to be in the header file. In the earlier in module 1, we have talked about source organization, where we said that all function headers must be in prototypes must be in header files .h files, function bodies implementation should be in separate .cpp files. But for inline function, this is not possible, because when an application sees the function prototype, unless it can see the body, how does it inline, how does it replace the body? So, for inline function, the body will also have to be in the header, and certainly the inline functions must not have two different definitions, because if it does have two different definitions, then two invocations will have two different behavior. So, these are some of the limitations or restrictions of function inlining that needs to be kept in mind. So, in summary, we have revisited the manifest constant from C. I am talking about the whole of module 6. So, we have revisited the manifest constants, and we have understood the notion of constness as is available in C++, and we have seen what are the advantages of const over manifest constant. We have also seen how const and pointer interplay. We have introduced the notion for volatility of data and seen how volatile data can be used in a C++ program. Next, we have revisited macros with parameters from C and shown how inline functions or function inlining can be used with advantage in place of macros, which solves a number of syntactic and semantic problems that the macros offer. Finally, we have also looked at the restrictions on inlining.